Okay, I think totally knows from Grapevine Calvin. Yep.
Oh.
That was
All right.
so messed up.
We are in section 9.1. So the first thing, we're going to do two things today. First one's composite functions. And then we'll look at inverse functions. First one's composite, then we'll look at inverse. So, the composite notation was the ones with the little circle. So it looked like this. Open circle like that. So we would read this as F composed of G. F composed of G. That's how we read it. So it doesn't matter what letters we use, but whatever the first one is composed of the second one. All right, so if I had B and then a C, we've got B composed of C. It does not matter what the letters are. The only thing that really matters is the order they're in. So just to kind of show you, if I change that to C then B, then it's C composed of B. Doesn't matter. Okay? Second one's always inside. So composed of means inside. So here's what we want to think of. We're going to see notation like this. I'll use my F and G. F composed of G of X. And what we want to do is rewrite it. So if we did F of G of X. So notice that G of X is now inside the F function. If it's composed of, it's made up of, it's inside it. That's all we're thinking of. So whatever this second one is, will be inside that first one. Are we okay with that? All right, so let's get a couple different functions up here. Let's say f of x equals 3x minus 1. And we'll go g of x equals 2x plus 5. Just make a couple up there. Now we'll look at a few different types of notations here. First, we'll start with some numbers. Let's go f composed of g of 2. Now you don't have to, but I would suggest doing the rewrite, because if you rewrite it like this, things start to look familiar. All right, so this means I'm going to put g of 2 inside of f. So when I rewrite it, I'm going to do f of g of 2. Now, the reason the rewrite's kind of nice, you already know how to do that guy right there. You know, to find g of 2, that means you put 2 in the g function. So pretend the f's not there. If I just asked you simply, hey, what's g of 2? Well, let me put 2 in there, figure it out. That's all I'm doing. All right? So it looks like something we've done before. So g of 2, see, 2 times 2 is 4, plus 5 is 9. That's 9. So now it's telling me to substitute the 9 into the f function. So f of 9, 3 times 9 is 27, minus 1, 26. So if I kind of do that rewrite, I just kind of work through it in stages. Let's get a different number here. Let's go g composed of f. Let's go negative 1. Again, doesn't matter which letter's first. I'm going to do my rewrite, which would be g of f of negative 1. And then you can kind of think of it as order of operations. I'm supposed to do parentheses first. I'm going to go to the inside. So my focus is right there, that f of negative 1. So that means I'm going to substitute negative 1 into the f. So I'd have negative 1 times 3 is negative 3. Minus 1 is negative 4. So now I'm finding g of negative 4. So now I'm going to substitute negative 4 into g. So I have negative 8 plus 5, negative 3. A lot of times on the composite functions, they look a lot worse than they really are. If I just work them out in stages, write it out and go in stages, it'll work. Let's go g composed of g of 5. Now this one looks even more strange because you have two g's there. It doesn't matter what letters are there. Do the rewrite first. So we're going to have a g on the outside, and then a g of 5 on the inside. So I'm going to go right to that inside and find this g of 5. So g of 5, 2 times 5 is 10, plus 5 is 15. So that inside now is now 15. And now I'm going to find g of 15. So I'm going to substitute 15 into the g function again. 2 times 15 is 30, plus 5, 35. Looking okay so far? Okay, we're going to stick with these same f and g values here. Just going to erase this. Instead of numbers, we're going to look at variables. Okay, stay with these same ones. It'd be like part 4. F composed of g of x. A lot of times we get a variable sitting there rather than a number. Still, just take the time to rewrite it. I'm going to put that g on the inside. F of g of x. Now I'm going to do exactly what it says. It says I need to have g of x in there. Not g of 2 or g of negative 1. I need g of x. Well, I know what g of x is. That's 2x plus 5. Just replace g of x. Now let's think about how to work something like this. This looks a little bit strange to us sometimes. For us, this should look easy. F of 2, put 2 in there. F of negative 3, put negative 3 in there. F of A, put A in there. Everybody agree with that? That's pretty simple, right? Review stuff, right? If I wrote, hey, we're going to find F of whatever, then we're going to put the word whatever in there. And whatever's in the parentheses. So this time, you're asked to find f of 2x plus 1. That means 2x plus 1 is going in for x. Whatever's in here is what's substituting for x. So we would have 3 times 2x, not plus 1, plus 5. Why I said plus 1. 3 times 2x plus 5, minus 1. Whatever was in those parentheses, this time it's an expression versus a number, that's still what's going to be substituted for x. There's not a whole lot we can do here. We can distribute the 3 and get 6x plus 15 minus 1 is plus 14. I could simplify it, but I can't combine everything. I don't have like terms. Look okay? If we switch the other way, let's go g composed of f of x again. So now we're going to put f on the inside. So g of f of x. I'm going to always start with my rewrite. The rewrite's nice because it helps me kind of see what I'm working with. So now I see this f of x sitting here. Well, let me put that in. That's g of 3x minus 1. So back to what we were talking about before. G of whatever's in here. So whatever's in here is going to go in for x in that g function. This time it's just 3x minus 1. So we're going to have 2, 3x minus 1, plus 5. So again, whatever we see here, it's going right there. Whatever's in those parentheses, that's what's substituting in. Now as far as the simplifying here, let's see, 6x plus 3. I'd have really 6x minus 2 plus 5, 6x plus 3. So a composite function just means a function made up of something else. Technically, every function is a composite function. This is a composite function. Look what it's made up of, x. What's this made up of, x? It's still a composite function. Okay? So when we're composing functions of another one, if I can just get this transition, get this written out, then I can see what to put in. Take the time to do the rewrite. Right? Our other part deals with inverse functions. So we need to be able to find an inverse function. Right? So some stuff from your past. Right? An inverse is a reflection over line y equals x. So the inverse is a reflection over the line y equals x. So I'll give you kind of a little sketch here. Let's see. I have a normal xy plane. And y equals x is actually line like 45 degrees. So it goes through the point 1, 1, 2, 2, whatever. So that's my y equals x line. So when we take a graph and we reflect it over that line, in other words, that mirror image, it's creating what we call an inverse. So let's say that this is my original graph. Again, just trying to make up a sketch here. Let's look at something like this. Here's my sketch. And I'm going to call this f of x. My drawings aren't going to be perfect, but we'll get the idea here. All right, so I'm saying, hey, that's some function f of x, whatever it is. Okay. If I reflect this over, that means kind of visualize this thing here flipping over that dotted line. So like if you were going to fold a sheet of paper right on that, and then what would the mirror image look like? The mirror image looks something like this. Again, I am not the best drawer. But something along those lines, probably down a little bit further, but you get the idea. Does that make sense? And again, hey, perfect. I don't draw very well, so I probably should have dropped it down a little more, but you get the idea. This thing's flipping over and going to become that. Okay? This is what we would call the inverse function. So the inverse would be that little -1 exponent. That's going to refer to our inverse. Okay? So really what has happened on an inverse is the points, the ordered pairs switched. So I'll kind of give you an example here. Let's say this ordered pair right here is 0, 5. Okay, we'll say that's 0, 5. That means that this ordered pair on the green one is 5, 0. Now, if it's drawn perfectly, it would look like that. But let's kind of see what's going on here. There's a cross on the y-axis. So I'm just saying it's up roughly 5 units. This one's crossing the x-axis. So that's why the y is 0. But look what really happened. The x and y switch places. Okay. I can even see it back on this guy here. And I'm picking the intercepts because they're kind of the easiest to view. let's say that this point is negative 6, 0. Well, that would mean that this point right here is 0, negative 6. So for an inverse, the x's and y's switch. Okay? That's going to create that reflection. Okay? So for an inverse, I'm just going to put up here above, switch x and y. The order pairs are going to switch, and that kind of gives you a graphical example there as far as what happened. If I did a point here, that'd be in the second quadrant, so that would be negative, positive. Well, the fourth quadrant would be positive, negative, so they're still switching. So let's look at how this relates to a function. If I said, find inverse, let's say number 1 here, f of x equals 3x minus 2. Okay, we're going to find that inverse. So I have f of x. We're going to work to find this guy here, f inverse of x. So first thing, all right, it's a two-step process. First step, switch x and y. Okay, here's my first step. I'm going to switch x and y. So that means I'm going to have x equals 3y minus 2. So I switched x and y. Notice we had f of x. To us, f of x is y. That's our function value. We're used to seeing that as y also. So I switched that to x. Then this x became y. So I've switched x and y. There's step 1. Step 2. Solve for y. So remembering what an inverse is, that may be kind of the new part. Switching x and y, hey, you know what? That's pretty simple. I can switch 2 letters. Not a big deal. Solve for y, we know how to solve an equation. So we just want this y alone. So move the 2 over. X plus 2 is 3y. My last step would be divide by 3. X plus 2 over 3 is y. And so now that would be my inverse function. F inverse of x would be x plus 2 over 3. There's my inverse function. So in other words, if we were to graph both the original f of x and the inverse, they would be mirror images over where this dotted line is. That's all it's saying. Okay. So 2 steps, switch x and y, solve for y. Let's go with something like this. Let's go f of x equals, and let's get something in like this. Let's go x cubed plus 7. So step 1, switch x and y. X equals y cubed plus 7. So we give you a couple different looks with these y's here. But step 1 still pretty quick. Switch x and y. Step 2, now the work comes in. I'm going to solve for y. So step 2, solve for y. I want to get this y alone. Means the 7 moves. X minus 7 is y cubed. I'm close to getting y alone. I got y cubed anyway. And so then if I want just y, remember that would be the cube root of x minus 7. If I want to go opposite of squaring is square root, so opposite of cubing is cube root. And I can rewrite this as f inverse of x equals cube root x minus 7. So this will be our standard notation for the inverse. So I can solve for y, and then I can put that inverse notation back in. Are we okay there? Let's go f of x equals 5 over x. That's my original function. Now we're getting some different type graphs here than we've seen. We know what a line looks like. These aren't familiar type graphs to us necessarily. That's okay. We're just working on trying to figure out what that mirror image is going to be. You'll do more of graphing of this kind of stuff in, say, college algebra class. So first step, switch x and y. X, 5 over y. Step 1's done. Step 2, solve for y. So a lot of times we get fractions in here. Remember, if we want to solve an equation that has a fraction, just multiply both sides by the denominator so we can get rid of the fraction. We don't solve equations with fractions. We get rid of them. So now xy is 5. Last step, just go right here. Y would be 5 over x. I divide that x over. I'm trying to get y alone. So now f inverse of x is 5 over x. Here's my inverse function. So what this is saying is, if I were to actually take a mirror image, a reflection of this original graph, 5 over x, and I reflect it over this y equals x line, I get the same graph back again. I'll get that same graph back again. So that inverse would be the same. So it looks a little bit weird. Now, if you think about it, kind of in a different sense, it wouldn't sound so weird. What we're saying is the reflection looks like the original. Okay? That should be true every time you look in the mirror. If you look in the mirror and you don't see yourself, we got some other problems we can't really take care of in here. But you should look like the original, right? So a graph, if you reflect it, can look like the original graph. Now, you haven't done a graph like this, but here's what it looks like. I'll just erase this. Here's what that graph looks like. Kind of give you an idea. Here's that same dotted line. So if I do that original graph in black here, here's the original graph. It actually has two parts to it. And you'll do this type of graph in a different class. Understand that? But just kind of picture that. There's my graph of 5 over x. Now picture it being flipped over that dotted line. The same thing will show up. It'll be the same picture. So it is possible to have the exact same graph. Just depends on what we're looking at. So now, see, I had green up here before. So there you go. Here comes the green one. It's going to be right on top of it. Something like that. Okay. So two-step process for the inverse. Switch x and y.